Well, I think because it's gone 9:30, so thank you for coming. We have several talks this morning on differential privacy. The first talk is on applying differential privacy to contingency behavior. This by Yosi and Rinott.
Thank you. So I'm going to start with apologies. There's not going to be any new theory here. What we wanted to do is to learn differential privacy and at the same time check how it applies to contingency or frequency tables. Such things were done also before, and I'll quote a little bit towards the end, given time. And this is ongoing work, so any advice would be appreciated. So I was going to skip this, but it's a way to pass some time and maybe some other people will come. So here is a story which is not very important. So recently there were complaints in Israel about elderly people after hospitalization. They have been approached by various organizations like nursing homes, and it caused great concern in police investigation. Actually, of course, we are sensitive to such things. I was surprised by the amount of excitement it caused in the media in Israel. And the question is, was this information obtained from de-identified data because epsilon and delta were too big or something like this? So you probably guessed that the answer is no. And the investigation showed that actually hospital workers sold the data to these agencies. And what do I learn from this? There's, again, nothing new. First of all, that there are adversaries and they're willing to spend money, as that was mentioned yesterday also. And certainly, at least this is what I think, and in general you may think otherwise. So the work which is being done here to protect published data is one of the links of privacy in the world, and maybe it's not the weakest link. There are many other links, so maybe we can compromise a little bit on epsilon and delta because data is leaking in some other ways, and there's no point in strengthening the weakest, a link that's not so weak. All right. So you've seen this 100 times, but I'm going to use differential privacy. So A and A prime are possible realizations of the data, and they are neighbors in the sense that you've removed one person, let's say, from the data set. And then the output, the probability that the mechanism which is randomized, the probability is with respect to M, which is a mechanism. So the probability to get some result S, if you start from A or A prime, they're very close. If delta is small, ignore it for a moment, and epsilon is small, and you can switch between A and A prime because neighborhood is a symmetric relation, so they're very close for any possible realizations of the data. So if epsilon and delta are very small, then you can't distinguish whether a person is in the data or not. So then you can't learn anything about this person and her data. And that's independent on what else had been published, which I call here the environment, a term I learned yesterday in one of the lectures, and scenarios. So it doesn't matter. It guarantees small epsilon and delta, guarantee everything. Now here's an exercise. So I was trying to understand differential privacy, and here's an exercise that I do for myself each time someone proposes a relaxation of differential privacy. I try to come up with some scenario of leakage, and then I have a way of thinking whether the relaxation is okay or not, and so forth. So here I'm going to talk about an idea that came up yesterday. So to determine the sensitivity only relative to the given data and not to everything potential. And let's try to understand what can happen then. And if you don't like my scenario or if it doesn't hold water, then just tell me. I wrote it yesterday after 2.5 glasses of wine and a long conversation about the history of Spain, right? So the scenario is this. Suppose so you may not like it, but if it holds some water, then you can probably modify it and come up with a better one. So suppose I know that either A or B are in the data set. I can invent stories how this would come about. And also there's other people are D, so the true data set is either D plus person A or D plus person B, two possibilities. Now I don't know this. This is a secret. I'm the intruder, and this is a secret. The reality is that D plus A is the true data set, and A participated, and B did not. Now, suppose what is being released is income. And income is not a secret here. The secret is participation being in the set D, because D is an interesting set, let's say, of people who have a certain disease. So that's what should not be leaked. But the information, whether it's income or height or something, that's okay. And that's released. So suppose M, the mechanism produces some B, which it selects at random. Then I compute the ratio, and I notice that I know the parameters of M, and I'm assuming that I know D about the rest of the people, and also I know A, and I know the income of B, so I can compute this ratio. Now, it may be if B, for example, stands for Bill Gates, I hate to mention him, but everyone does, so then it may be that, and A is a more normal person, then maybe that this output that actually came from a normal person could not come if Bill Gates is in the data set. So then this ratio is large. If this ratio is large, is a question how you use it. If you're Bayesian, use it as a Bayes factor. If you like to do likelihood ratio tests. But in any case, you can now learn with good probability that A is in the data set, and you've learned something about someone who contributed to the data set, and the person who helped you is Bill Gates, who's not in the data set. So I also learned that he's not in the data set, but he didn't contribute, so we don't care about that. So the point is, because you didn't take Bill Gates into account and protected only your data set, there is intrusion. Now you can decide this is far-fetched, or you can say, I can make versions of this which are more unacceptable. Any comments on this? Okay, so let me go on. So the question that we raised, now I'm getting to our work. So the question that we raised is, can we use epsilon and delta to compare different release schemes and say this one guarantees more than this one, and of course there's a question of utility, which I'll talk about a little. So differential privacy is worst case analysis. So comparisons in terms of the worst case are very common, but I think it's somewhat debatable when you compare algorithms. If you have an algorithm, so most of complexity theory is based on worst case analysis. There is some average case analysis also. So worst case analysis means I compare two algorithms at their weakest point, but the weak point may be very rare and you may or may not like it. But in cryptography, and also in this area that we are talking about, there is an adversary who is looking for the weakest point. So here it may be more reasonable to look for bad cases or the worst case. But I think one can argue about this point. Now I want to make another point, and I'm curious what you think. If epsilon and delta are not small, then in some sense the environment may matter. If I identified, for example, that guy A from the previous slide is in a particular set, then now I know that he's in a particular set. But suppose there's not, in the environment, there's nothing about this set of people, then maybe the risk is smaller. But if in the future someone will say, oh, the people in that group were did not only have this disease, but they had a very high level of that disease, then now in the future I find that I learned more. So what I'm saying is epsilon and delta large, you have to be more careful in saying it doesn't depend on scenarios, it doesn't depend on environment. By the way, the colors are words that I would like you to remember. That's what they mean. An environment is green, hopefully. And so what I'm saying is, if you're actually settled because of what I said in the beginning about epsilon and delta on epsilon and delta that are not very small, then you have to take the environment into account. So if I'm considering one data set to release, then it has its own environment, and then I can compare different release schemes, and I think it makes sense. But here I'm talking about releasing data, I don't know, on some people in Israel and on some kangaroos in Australia, and the environment is very different. Then maybe the comparison in terms of epsilon and delta, and to say the Australians are more careful, it may, who knows if there's more data about what the environment is, if there's more data about kangaroos. So this means that since we are going to use epsilon and delta that are not very small, we have to restrict, I think, our comparisons. Now we get more technical. So I have a set of tables. I have a list of frequencies. I just put them in one big row. I stack them one way or another. And this is my list, A1 to AK. So K may be very large. This comes from a frequency table. I don't have time to discuss whether it's a sample or a census. Let's assume that this is census data. And and these are frequencies of some cells. They may be inner cells of a table, or they may be marginals. I'm in my list that I'm about to publish. Maybe there are inner cells and also marginals, because if I only perturb inner cells and let the user find the marginals by adding, then maybe there will be too much noise for him on the marginals. So my list could be complex. So is this clear? So here is an example. Suppose I have a three-way table with frequencies x, I, j, k. And suppose I'm considered to release everything, all the marginals. Then these are the inner cells, the collection x, I, j, k, all of them. And these are the two-dimensional marginals. You sum over I and j, k. There are three of them because you sum over I or j. And then these are the one-dimensional marginals. And again, it depends on I or j or k. So altogether, there are 7 big collections. Now, in each collection, each individual appears only once. And in the whole collection, which I call A, this A here, it's easy to see that each individual appears 7 times, 2 to the 3 minus 1, because I don't publish the sum of everything. That's just the population size. That's the minus 1. So D is purple, so try to remember what D is. So it's the number of times each individual appears in my collection that I'm about to perturb. And if A is just the inner cells, then in a contingency table, everyone appears only once in one of the inner cells and not in others. So then this purple D is 1. Is this clear? I'm sorry for asking, is this clear? I've been teaching for too many years. So. And I know the students don't like it, but they don't like to be asked that question. So let's assume for a while, but it looks like I won't have time to get to much more, that D is 1. So we're thinking right now that we are publishing inner cells of a table, and then each person is in one of these cells, and that's it. And what we are doing, there is a mechanism M which adds randomization, any probability that will be written is with respect to that. And what it does, it applies to something in A. This A is my list of possible data sets, which doesn't include people over 3 feet, I think 10 feet was mentioned. I don't think in terms of feet, so I don't know. But I guess 3 feet is a midget. So, and then the perturbed list, I'll call it B. And let's assume that it has the same structure. So we publish, there's a table, and we publish the table perturbed, but with the same structure. So I can assume that B is in the same space, but it's not very important. Now, what we wanted to do is to look at standard ways that people publish data, and we followed a pattern, but not precisely, of something called Table Builder, which came out of Australia, but apparently is used also in Europe. But there's nothing very special about it. They have some principles which everyone can understand. So the first principle is that the whole data set is perturbed once, and then can be released as a whole, or if you want, you can ask for a part of it and think that you're doing something interactive. But this is non-interactive perturbation. You perturb the data set, then you keep the perturbed one, you can ask for the whole of it, but if it's too much data for you, you can ask for parts, then for other parts, see what you got, but it's non-interactive. Now they have, in this Australian table builder, they have a principle that one can definitely dispute, perturb A to be in each cell independently. It makes life very simple. By the way, these are not all consistent also, but these are some desiderata. So they want unbiasedness, but if you have a 0, you can't perturb it unless you keep it. There will be bias. But so let's say unbiasedness or approximate is desirable. They want to truncate, so if you don't truncate, maybe there will be a real outlier, and then if you kill it, then you don't know what you've done to the differential privacy. So if you can find a scheme that from the very beginning takes this into account, it's better. So this will, of course, will be good for utility and just for looking for the tables to look reasonable. Let's ignore this one. They don't want small, but let's ignore it. Another principle that they have, for some reason that they don't specify, you can try to guess what they had in mind, is given A, I generate B with a certain variance and on a certain support, but I want to choose a distribution that has maximum entropy. So intuitively, you fix the variance, now you want maximum entropy. So you probably know that maximum entropy for a given variance in general leads you to the normal distribution. Since everything here is discrete or discretized, because we are talking about count data, then actually maximum entropy has to be computed numerically with Lagrange multipliers, but it's easy, and you can compute the distribution under any conditions that you decide, and they're going to look like discretized normal, which are not necessarily optimal. And so it's not clear why this principle, and maybe we'll be able to tell them that they should abandon it, but I don't know. And then there's one other principle. If two cells, so I have A1, A2, these my cells that I'm going to perturb, if they represent the same group, then it should be noticed and they should be sent to the same perturbed value so that I don't get repetitions which I can average. So I guess it can happen that the same group of people appears in different cells. So suppose in this here I ask for the group of people who are between the age of, I don't know, 34 and 34 and a half, and then I ask 34 and 34 and a quarter, and it may be the same group, but it's defined differently and maybe you didn't notice. So they have this principle which they consider important. Now we need to talk about loss functions, because we are statisticians, so we like loss functions, and much of statistics is based on loss functions. So you can say, how much do I lose if I publish B, but the data was actually A, so here is one measure L1, here is one measure L2. These are the most standard in statistics, actually. And here is another one, which takes the roots. I called it L3, but you probably should have called it L square root of 2 or something. And I actually like it in some sense. It's reminiscent of something called Hellinger distance, but never mind. So what does it do? If you perturb 0 to 4, just think about one cell, then the square root is 2 and 0, so you pay 2 in the loss. If you perturb 100 to 144, the root is 12 to 10, you pay 2. And if you perturb this, 10,000 to 10,400, again you pay 2. To me this makes sense. If you're using L1, then a perturbation of 1,000 to 10,400 is terrible. But I think these are more or less comparable. Do you agree? And so I tended to like this loss, and when I was learning what can be done, I looked at it. Now we want to measure utility relative to such losses, but also relative to models. So the idea of these bureaus, I think in general, is that people will take the perturbed table, hopefully they look not too dissimilar to the original data, and they will analyze them as if they are the data, not taking the perturbation into account, which could be done, but I heard from people here that it's not so easy, right? So the question is, suppose I have independence in my original table, now it's perturbed, will independence survive or not? This had been looked at by other people in different ways, and I'll talk about it in the end, maybe. So utility is just negative of the loss. Everyone does that. So people in economics, in game theory, and also differential privacy people, they like to use the word utility, but they're the same to me. And now everything that we do is in terms of something called exponential mechanism, which I learned from the privacy book, which I cited in the very beginning. So what it says is you have A, which is a big vector of frequencies, and you want to perturb it to B, and this B is chosen with some probability, and the probability, there's a parameter eta, there's the utility now, which is negative the loss, and there is a sensitivity which is defined here. You've seen it. Unless you ask me, I will not talk about it now, but it was part of the example that I gave in the very beginning with Bill Gates. So because the question was, how do you compute sensitivity? Do you compute it only on your data, or do you compute it including Bill Gates, who's never in any data set? So this mechanism attaches higher probability to lists with higher utility, as you can see here, because it appears in a positive way up here. So you might think that if you have in mind this Hellinger type loss, then maybe this will be an efficient way to go for that, and if you have in mind another, and that's what I thought when I read this idea for the first time. Now, if you assume that your loss is or utility is a sum, then just write it down, and the sum, e to the sum, becomes a product, and you have independence, which is what the table builder kind of wanted to do anyhow. So we are in agreement with them. And then each AK goes to BK with some probability, and these probabilities are determined like this. And epsilon and eta is a parameter, and for different etas you'll get a different epsilon. There's a direct connection, which I'll explain in a minute. So you should understand that if eta is very small, then all these numbers are very similar and you get a big spread. And if eta is big, then in the examples that I gave, the perturbations will be smaller. So a small delta means more perturbation. Okay, now I'll quote one theorem, which is in the book. If you use this method, then your perturbation is proportional to this, which you remember from the previous slide because it's blue. So so then you get differential privacy epsilon. I define differential privacy with epsilon and delta. If it's just epsilon, it means that delta is 0. So so this mechanism will guarantee. So notice that the delta here, if you remember the blue formula from before, notice that the eta, I think it was eta, right, is epsilon over 2. So to get epsilon, you need eta epsilon over 2. That's kind of not good for us. We would have liked to get a big epsilon. We get a slightly smaller epsilon, but that's life. Okay, I had the courage to put the proof because it's extremely easy. All you have to do is compute this ratio. But the ratio is just the perturbation, of course, standardized. It has to be probabilities. So the ratio is this divided by this directly from the definition. And then actually, if you divide this one by this one and this one by this one, you see in a minute that each one is less than epsilon over 2. And that's how you get e to the epsilon. So the proof is really one line. And it takes into account this thing here, that you've bounded the sensitivity. So here is another theorem that we will use. So suppose, as in all our examples, that your utility is a function of the difference. This was the case for all our... maybe it's not true for U3, for the third one, because there's the root. Yeah, it's not true. So it's true for L1 and L2 and any L something, but it's not true for the Hellinger. So, which I'll say something about later on, perhaps. And now the random mechanism does the same, but now there's only epsilon, so we're in a better shape. You don't divide by 2. And we allow AK minus BK, we allow a truncation, so you never go beyond that. And then I need, so otherwise you don't get a B. You get B's only satisfying this. But I need now another condition. If A prime cannot get to B, the probability is 0, and A is a neighbor which is allowed to get to B, it has to be allowed to get to B with a very small probability. Let me explain this here. Suppose I'm looking at one cell, and this is, let's say, A, some frequency, and this is A prime, some other frequency. So think about one cell. And A can go to A plus M, because we are allowed to go up to M to the right and to the left. But A prime can, the maximum that A prime can go to is here. It can't go to A plus M. So if I see A plus M, I know something. It must be A and not A prime. That's kind of bad. So I want the probability that A will go to A prime to be small. So I'm compromising a bit, but I'm allowing, with small probability, to get extreme values which are revealing. And that's the delta. So you must have such an extra condition which we have to take care of. And with this you now get, so if the probability is small, as written here, then now you get differential privacy with epsilon and not epsilon over 2. So in this sense you're better, but you pay the price of delta. So the famous perturbation comes from L1. If you just take the blue exponential mechanism and apply it to the loss function L1 or to the utility U1, then you get these formulas. You get that the perturbation in each cell satisfies this, which is a Laplace distribution. And you can bound, by the way, M could be infinity, and delta is 1 because a person appears in one cell, so the two neighboring tables can differ only by 1. So delta is 1, and you get these formulas. Everything can be computed explicitly if you know the formula for a geometric series, and everything is easy. So for example, if you agree to epsilon equals 1 and take m equals 10, then this is delta, which is a fairly small number. But there are different numbers. We have all sorts of tables. I don't know if I'll get to this. If you take U2, which was squaring, and you still want to do this, then now delta becomes some number that depends on m. So now you can't take m to be infinite. You must truncate if you're perturbed by normal for such stories. And then the probability is proportional to this. It's not equal because I didn't write the normalizing constant. But this is a discrete truncated normal distribution or perturbation. Okay, so you can consider the normal. So as was pointed out, this theorem does not apply to the Hellinger type thing. There are some theorems that show that Laplace work very well under some circumstances, but that there are other results that show that this cannot be extended very universally, but I don't have time for this slide. So there's good reasons to think that Laplace is very good, but I will skip it. Here I can show you some numbers. So what we did, but we are not the first to do things like this, and I'll say something towards the end. So this is a table which contains a large number of people, 10,000, and we we bounded, this m is the small m, so we allowed to go plus or minus 10, and the table was generated by Natalie, assuming independence. She created the table in a random mechanism that assumes independence. It's a two-way table, independence of the attributes. The true value for this particular example, the p-value for testing independence in the standard way, was this number here, which may be 0.8 or something. Can you see anything here? Can you see this? So I'm guiding you here. There's a line here which is at about 0.8, which means the p-value for testing for independence was about 0.8 for this particular example. If you perturb with epsilon, which is equal to 0.5, then the p-values will be within here. So actually most of them will be smaller, but most of them will not reject independence. So you'll still have agree to independence. You say, I don't have reason to reject. And then if epsilon is 1 or more, then the p-values get closer and closer to the true p-value for this table without perturbation, and the p-values get very large, and you'll certainly not reject. So it's working reasonably well.
Is that with large counts as well? The average cell size here is
Yeah, this is a table with many people.
zeros.
Yeah, this is a big table that comes from a large population or large sample. But this is just a simulation. If you apply perturbation by the normal, the situation is worse, and here you see that the p-values are smaller for epsilon 0.5, and you may reject independence wrongly because of the perturbation. If you allow a bigger epsilon, the situation gets better. And now I'll show you another. We have plenty of tables. So what this table shows is the following. Suppose you take epsilon to be 1 and m is again 10, and you use the Laplace mechanism. Then we just calculated. There's an explicit formula which I showed before. And so the probability that 0 remains 0. Oh, I forgot to say, it was written, but I didn't say, when you do these perturbations by Laplace, you may get negative numbers. If you perturb 3 with plus or minus 10, you may get negative numbers. Then, of course, you just throw them to 0. And that's called post-processing, and that's, that doesn't do anything to differential privacy. By the way, I don't know, I was going to ask, since you're not asking questions, I'll ask the audience. In many tables, there's pre-processing. So before publishing, the Bureau will do certain things, and the question is, if you have a table that you want to protect, and you do some well-defined pre-processing, and then you apply differential privacy, maybe the pre-processing...
How do you add M to work?
So maybe the pre-processing by itself seems like it's hiding, but then combined with something else, it's hard to tell what happens. But it depends on what the pre-processing is. If the pre-processing itself is a good perturbation, then it helps. But we don't have time to go into this. But what I'm saying, so coming back to this, the probability that 0 remains after pushing negatives to 0 is very high. The probability that 0 is either 0 or 1 is very high if epsilon is 1. Epsilon is 1 means that you've compromised on the protection. And if you look at 0 and you ask, is it perturbed up to 2, then the probability is very high that you won't get beyond 2. So this looks like a reasonable perturbation if you take 1. Now if you take 0.1, you can see that the numbers are not as good. And we have here the numbers for any perturbation. It's easy to see that they all get equal from a certain point on, because because there's no difference. Once you perturb 20 or 25, you go plus or minus 1, it's the same. So my kind of superficial impression here is that such intervals you add or subtract and then push to 0 if needed, 2 or 3, so maybe it works okay if epsilon is 1, maybe if epsilon is 0.5. I put here only the more extreme case of 0.1. Some people may say that even 0.1 is not good enough, so my impression is that it could work. So now I didn't think I would have time to treat the case of multi-way tables in which the purple D is no longer 1. So you may remember this, that I put a big array. I can treat it in different, so let's just talk about this and then I'll say something else. So you may remember this. So I form the inner cells, marginals, all marginals. In each collection separately, there are 7 of them here, D is 1. So I can do what we did before and publish the first collection, the second, and I have 7 such collections. And in general, if you do this, so you publish an array and each component is masked, then the epsilons add up. So now you can decide, so each one of them you can choose the epsilon. Maybe two-way tables are important for you, so you have some flexibility. You can mask them with a smaller epsilon and other tables a higher epsilon. So there's a lot of flexibility. And you can do other things. As I said before, the purple D is T to the 2 minus 1. You can just treat it as one table, and then you'll have a larger delta. So I want to finish and say something else. So Steve Feinberg had looked at this, and I don't know if you know, but Steve Feinberg died yesterday. So I got a message from Israel. He was, so I'm sorry to say it this way, but in his honor, I will say 2 words and then probably the organizers. So he was very curious about differential privacy and other things, and Steve was a very critical person. He wouldn't buy something just because he thinks it's smart. So one of the things he did was he looked at frequency tables and applied differential privacy techniques to them and tried to see the conclusion. Because of his own taste, by the way, I learned frequency tables from his books. There's the famous Bishop Feinberg Holland, but there are other books that he wrote. And of course he liked what's called log linear models, which in particular include the question of independence. So he tried to see whether following perturbations, log linear models survive or get killed. He also worried, if you notice about the perturbations here, the total population or sample size, if you perturb independently, may change. And he worried about a lot of details. This is he did joint work with other people, and they went quite deeply in this. I'm basing my knowledge that he died on a message from Danny Pfefferman, who some of you know. He's actually what's called chief statistician or something in Israel. There have been cases where messages were wrong, and in the Jewish tradition, this is a guarantee for a long life. So if the message is wrong, let's hope, but it seems pretty reliable. So with this sad note, I'll finish the talk.
A bit shocked, I think we all are, after hearing that. Maybe the organisers, we can talk at some point, decide if maybe they want to say anything about it. But maybe for now we can just ask some questions and gather our thoughts. Any questions?
Yosi, I really apologize for the question, but is the main thrust of the talk the savings of the factor of 2? Or
No.
so what is the main point that you're making?
I would say that the main point is we wanted to see if the perturbations are bearable relative to reasonable epsilons. And my conclusion is that there's a good chance that they are, contrary to what Steve Feinberg thought, I think. At least in one or two papers that I know. He may have evolved, and I don't know everything about this. So I would say that my goal in this work is first I think this way we began to understand differential privacy better, to see how it applies, and perhaps to be able to advise these agencies, for example, forget about maximum entropy, it's better to do this, it's better to do that. And you apologize, and I agree that it's a humble goal. So we didn't
There's a lot of information there. A lot of it is on things that I don't know so much about, and I was having trouble keeping track of what was the message I was supposed to be receiving.
I see.
Also, I was excited that you started to talk about the Hellinger distance. Do you have any theorems about differential privacy using that loss measure? I've
No,
not
but-
seen any other work that uses it.
You know, I'll do what sometimes people do. I'll answer a slightly different question, and I'll explain. Politicians do. I'll explain why I think, this is one of the things I think I learned from this. So Hellinger performs poorly. So the fact is that if you use Laplace and see and then compare utility in terms of Hellinger, then Laplace does better than Hellinger. Although perturbation seems to be directed towards. So why is this? So Hellinger, by the way, the delta is 1, so you can apply it without an m, and then the first theorem applies, so it can work. As pointed out, the second theorem doesn't apply. So I think the reason is the following. So in the Laplace, this delta is 1, but it's 1 throughout. So in some sense, the worst case is the typical case. Hellinger's square root is a concave function that looks like this. So if you compare two neighbors here, then the difference is 1. But if most of your data is here and you're protecting by 1, then you've protected, as people noticed, you've protected too much because your real data is not there. So there's a question what to do. But differential privacy has...
Sounds like a great setting to try the proposed test release framework.
we have to talk about it, I guess,
Okay.
later. But my point is that the thing I think I learned from this is that if a release method or if an algorithm treats everything more or less equally, then it has a better chance. And if a release mechanism pays particular attention to a rare or not so rare, but here you're protecting against the worst case, then it's likely not to be so good. So my feeling is that this is why the Laplace is such a winner. Please.
And maybe just one more, because we're running over. Gillian, I think you've been waiting.
So I was very upset about what you said about Steve Feinberg. I hope the message is wrong, as I had an email from him at 8:15 last night about a paper I was submitted, and I hope it didn't kill me.
Look, I said I'm based on one email, and let's hope I'm wrong.
I just wanted to make a small point about the Hellinger distance. I've been using something equivalent for looking at the utility of something similar to look at the utility of synthetic data, but instead of taking the sum of the absolute differences, I've taken the sum of the squares of the differences, which in statistical parlance I think is called the Freeman-Tukey distance.
I didn't know that.
It's the same. I think it's the same, but you took the sum of the absolute differences.
Yeah, the true Hellinger is to square and then take square root.
Yeah, but I just wondered why but you don't square the distances, do you? You just take the sum of the absolute.
I could. There's no answer to this. It's an arbitrary choice, which seemed reasonable. I played with some examples and chose this one. You could square them, but then again, you're paying a different.
It's a different.
But I can't take a square root of everything like Hellinger, because then I lose the independence because it's no longer a sum.
It's an obvious thing to do because it stabilizes the variance of the counts.
But you know, the square of the loss and the loss, they are related in a simple way, and it doesn't matter for me.
That's what weighting we want to put in.
Yeah.
We really have to move on. Sorry, maybe if you leave questions more for the break, because we are overrunning. Geordie, I think you're next up.
Oh, I just